Imagine a bathtub starting as ordinary earth, then surviving crushing, shaping, glazing, and 1,000-degree fire. And here's the strange part. The elegant white surface begins as a mixture of minerals that looks almost worthless. One wrong ingredient, one trapped bubble, or one tiny crack can ruin an entire expensive bathtub. So how does a mountain of raw minerals become something smooth enough for luxury bathrooms? We begin where every ceramic masterpiece begins, with carefully selected earth, minerals, water, and extraordinary control. Ceramic bodies commonly combine clay or kaolin with quartz and feldspar, each performing a completely different job. Clay provides plasticity, quartz helps control shrinkage, while feldspar acts as a flux during high-temperature firing. The research formulation can use roughly half clay, with quartz and feldspar supplying much of the remaining ceramic structure. But factories rarely follow one universal recipe. Body composition changes with the product, equipment, and desired performance. That flexibility matters because a huge bathtub behaves very differently from a small ceramic cup. Before shaping begins, the raw minerals must be crushed until the particles become consistent enough to mix predictably. Huge steel mills then grind those materials with water until the mixture becomes a controlled ceramic slip. Inside the mill, hard mineral particles repeatedly collide, breaking down until the suspension reaches its required fineness. Now comes a critical secret. Ceramic particles must be controlled because particle size affects drying, firing, and final strength. The liquid mixture then passes through screens and magnets, removing unwanted particles before they can damage the finished surface. Air bubbles are another enemy, so controlled mixing and de-airing prepare the slip for large-scale forming. And this is where the raw material finally starts behaving less like mud and more like engineered ceramic. Some facilities use casting, where liquid ceramic fills a shaped mold and gradually builds the bathtub walls. The mold absorbs water from the slip, leaving behind a growing ceramic shell along its inner surface. The thickness must stay remarkably uniform because uneven walls can create distortion during drying and firing. Once the ceramic shell reaches the target thickness, excess slip drains away, leaving the future bathtub surprisingly fragile. At this stage, it looks nothing like luxury, and the slightest careless movement can destroy hours of controlled processing. Now the factory faces its first major transformation, removing enough water without letting the ceramic warp. Drying too quickly can create internal stress, so industrial chambers carefully control airflow, humidity, and temperature. And here comes the first cliffhanger. The bathtub is shaped, but it is nowhere near strong enough to survive its final transformation. Before the fire, workers carefully remove seams, smooth edges, and correct tiny imperfections that machines may miss. A smooth edge may look simple, but it determines how the glaze flows and how the final surface feels. Then the entire piece enters a controlled firing cycle where chemistry, heat, and time begin rewriting the material. Industrial sanitary ware research commonly studies firing around 1200 to 1280 degrees Celsius. That's hotter than a domestic oven by an almost unimaginable margin, and the ceramic structure starts changing permanently as temperature rises. Chemically bound water leaves the clay, while minerals begin forming new ceramic phases. Quartz, feldspar, and clay-derived phases interact as the body gradually becomes dense, rigid, and dramatically less porous. Researchers call one important crystal phase mullite, which contributes to the microstructure of fired ceramic bodies. But the kiln cannot simply blast everything with heat. Temperature must rise and fall according to a carefully controlled curve. If the heating cycle is wrong, cracking, warping, bloating, or unwanted deformation can appear after hours of work. And because large bathtubs have long surfaces, even tiny thermal differences can create major dimensional problems. After firing, the once fragile body emerges hard and pale, ready for the layer that creates its famous glossy appearance. That layer is glaze, a carefully formulated glass-forming coating designed to melt, flow, and fuse during firing. Workers measure glaze carefully because its chemistry controls color, melting behavior, surface texture, and final for a luxury bathtub. Consistency matters because one uneven spray pattern can become obvious across an enormous curved surface. Appearance. Automated sprayers can move around the bathtub while maintaining carefully controlled distance, angle, and coating coverage. The spray looks almost magical, but underneath that mist lies precise control of flow, pressure, and timing. After coating, the bathtub returns to the kiln, where the glaze transforms from powdery-looking slurry into glassy brilliance. As the glaze melts, surface tension helps it level, creating the smooth, reflective finish we associate with premium ceramic ware. And here's the payoff. A surface that looked dusty moments earlier can now reflect the factory lights like polished glass. But the journey is not over, because cooling can create its own hidden stresses inside the ceramic. Controlled cooling lets the body and glaze settle together instead of fighting each other as temperatures drop. Only after cooling can inspectors finally see whether the entire transformation succeeded, and this is where thousands of hours of material science meet a human eye. Searching for one imperfect reflection point, one tiny pinhole, blister, crack, or glaze defect can mean rejection, even when the bathtub looks perfect from across the room. The rejected piece may return for evaluation, but serious defects usually cannot simply be polished away. Now the factory has a new challenge, proving that this beautiful object can survive real bathroom life. Modern ceramic factories combine human craftsmanship with sensors, automated handling, digital measurement, and machine vision. A laser scanner can sweep across the bathtub and compare its actual shape against a digital reference model that reveals dimensional deviations invisible to ordinary eyesight, especially around long edges and complex curves. Machine vision can also search glossy surfaces for irregularities that human inspectors might overlook under ordinary lighting. Sensors can measure temperature, humidity, coating conditions, and process variables long before defects appear. Robotic arms handle heavy molds and finished pieces, reducing repetitive lifting and keeping movements consistent. Yet robots cannot replace every decision, especially when a skilled worker notices something the sensors cannot understand. That human judgment becomes especially valuable when subtle surface texture looks technically acceptable but visually wrong. Luxury manufacturing is not only about passing measurements, it is about making the finished object look and feel deliberately perfect. Inspectors check dimensions, glaze quality, drainage openings, edges, mounting points, and the overall integrity of the ceramic body. Dimensional tolerances depend on the manufacturer and product specification, rather than one universal bathtub number. That distinction matters because different ceramic products follow different technical standards and testing requirements. For ceramic standards, laboratories may examine properties such as water absorption, strength, dimensions, and surface performance. In vitreous sanitaryware research, fired bodies can reach water absorption levels at or below about 0.5%. The low absorption comes from vitrification, where heat creates a dense structure with very little connected open porosity. But density alone does not guarantee perfection. Glaze adhesion, thermal compatibility, and hidden internal flaws still matter. Testing can include controlled impacts, thermal cycling, surface inspections, dimensional checks, and other manufacturer-specific durability evaluations. A thermal test can repeatedly expose ceramic samples to changing temperatures, searching for weakness caused by expansion differences. The goal is simple: discover weaknesses inside the laboratory before customers ever discover them inside their homes. Now comes a fascinating moment. Technology has measured everything, yet a human inspector still makes the final visual judgment. That combination of machine precision and human perception is what turns industrial repetition into luxury craftsmanship. But before this masterpiece leaves the factory, another question remains: how many can the industry actually produce? Here's the surprising truth: ceramic bathtubs occupy only one niche inside the much larger global sanitaryware industry. Unlike many mass-market tubs made from acrylic, steel, or other materials, ceramic tubs target a distinctly different design category. That means production volumes for ceramic tubs cannot simply be confused with worldwide bathtub production as a whole. The broader ceramic sanitaryware sector includes toilets, wash basins, bidets, urinals, sinks, and specialty architectural pieces. Countries with major ceramic industries include China, India, Turkey, Italy, Spain, and several other manufacturing hubs. China dominates enormous portions of global ceramics manufacturing, supported by vast industrial capacity and extensive domestic supply chains. India has also developed major ceramic manufacturing clusters, combining large-scale production with increasingly sophisticated automated equipment. Turkey is another major ceramic manufacturing center, especially known for large Scale tile and sanitary ware production. Italy and Spain emphasize design, advanced ceramics, energy efficiency, and high-value architectural products alongside large industrial output. But global ceramic production has changed dramatically over the last 50 years as automation replaced many repetitive manual operations. Older factories relied heavily on manual molding, handling, inspection, and kill control compared with today's sensor-rich production systems. Today, digital monitoring can follow temperature curves, material batches, machine states, and inspection results throughout production. That creates something factories decades ago could barely imagine: a digital record following each production batch. And that traceability becomes powerful when a defect appears, because engineers can search backward for its likely cause. Energy is another major issue because ceramic manufacturing depends on intense heat for firing and vitrification. Even small reductions in firing temperature can matter when enormous industrial kilns operate continuously. Ceramic manufacturing also consumes substantial natural resources, from minerals and water to fuel and electricity. Modern facilities can recycle process water, recover heat, reuse selected ceramic waste, and capture useful material from production streams. That does not make ceramics impact-free, but it can reduce waste and improve how efficiently factories use resources. Now imagine multiplying this process across thousands of factories and millions of ceramic products every year. That is why the ceramic industry represents a huge global manufacturing ecosystem rather than one simple bathtub assembly line. Did you know ceramic firing can reach temperatures above 1200 degrees Celsius in sanitary ware research? Did you know some porcelain research fires materials between roughly 1200 and 1400 degrees Celsius? And did you know researchers can deliberately adjust particle size to influence firing behavior and final ceramic properties? The future may bring smarter kilns, more efficient materials, automated inspection, and increasingly personalized ceramic bathroom designs. Instead of producing one identical bathtub endlessly, digital manufacturing could make premium designs with greater variation and precision. Imagine scanning a digital design in the morning and watching a customized ceramic masterpiece emerge days later. That future depends on controlling the same fundamentals that shaped ceramics for thousands of years: earth, water, heat, and skill. And that brings us back to the beginning, where an ordinary mineral mixture waits to become something extraordinary. From quarry dust to polished curves, every stage exists because ceramic manufacturing leaves almost no room for careless shortcuts. Every curve hides measurements, every shine hides chemistry, and every strong surface hides a carefully controlled firing cycle. And after all that complexity, the final product simply waits, quietly in a showroom, looking effortless. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.